So the final talk of this conference is given by Thorben Tröbst, a former student of mine, by the way, now at UC Irvine.
Yeah, thank you very much. Let me start the screen share. Okay, and okay, I can draw as well. Okay, can everybody see the screen?
Yes.
I think so. Okay. All right, then welcome to the last talk. I will talk about my paper with Vera Traub on capacitated cycle covering. Okay, so I'll start by briefly introducing capacitated vehicle routing, which was the main motivation for us to study this topic. So the capacitated vehicle routing problem is a very classical combinatorial optimization problem where you are given a finite metric space, or you can think about it as a complete graph with metric edge weights. And there's one special vertex, often called S, which is the depot. And the goal is to compute a bunch of tours, that is cycles that visit a set of points and go through the depot, such that a capacity constraint is satisfied. So every point out here, except for the depot, has a certain demand. And you want that the total demand in each tour is bounded, say, by 1. And so the goal is to compute a collection of tours that cover every single point, such that the total distance is minimized and the capacity constraints are satisfied. So to make this more formal, the input to this problem is a complete graph. And this graph has a special vertex S and metric edge lengths. And it has vertex demands. And we normalize the demands to be between 0 and 1. So there are some rational numbers between 0 and 1. And the task is to compute a set of cycles, which we allow to be degenerate, which means that we allow cycles of length 2, such that every single point is covered by one of the cycles. Every cycle contains the depot. The capacity, or the total demand that's served by every cycle is at most 1. That's the capacitated part. And the total length is minimized. So this is the classical capacitated vehicle routing problem. And just to give like a short history on this problem, it was introduced by Danzig and Ramsor in a paper titled The Truck Dispatching Problem back in 1959, where they did some integer programming to solve some very small instances of this problem. And there's an approximation algorithm for this problem, which is a 3.5 approximation, which is by Alton Kimmer and Gavish from 1987. And this is based on some prior work by Rinoy Khan and Haimovich from 2 years earlier, which considers the case where the demands of all vertices are the same. And recently, there have been some small improvements on this approximation algorithm. So, for example, there's this work by Bompadre et al., which considers the case where you don't have uniform demands, but demands with the same small fractional denominator. And there's some work, for example, in vehicle routing in special metrics, such as on a tree or on a line. That's more recent. But in general, the problem has not, or the approximation ratio has not been improved in, well, over 30 years now. This is quite a difficult problem. And we were interested in this problem, but since, as I mentioned, it's been proven to be quite challenging to improve this approximation, we instead considered not quite a relaxation, but a very closely related problem, which removes one of the difficulties in the capacitated vehicle routing problem. So you can kind of think about the capacitated vehicle routing has 2 components. On the one hand, you have kind of a TSP-like component of building short tours. But on the other hand, every tour that you create, you add these edges to the depot. And this is kind of, you can think about it as a kind of opening cost of the tour. And so what we did to simplify this a little bit is we introduce this problem, which is called capacitated cycle covering, which is very similar. Namely, you still have a complete graph, you still have metric edge lengths, you still have vertex demands, but instead of having a special depot vertex, which every tour needs to connect to, you instead have an opening cost, which you have to pay for every single cycle that you create. So then the task is to compute, again, possibly degenerate cycles in this graph, such that every vertex is contained in one of those cycles. The capacities are bounded, so the total demand of each cycle is at most 1. And now the objective that we're trying to minimize is a linear combination of the total length and the total number of cycles. So that's where this opening cost gamma comes into play. So the main change from vehicle routing is that we essentially replace the non-uniform opening costs in the vehicle routing problem, which come from connecting to the depot, by uniform costs, which makes the problem simpler. Okay, so here's an example. So let's say you have your finite metric space is just a Euclidean plane with some points in it. And let's say the demand is uniformly 1/4 everywhere. So you can put 4 points into a cycle. Then depending on what the value of gamma of the opening cost is, you can get different kinds of solutions. So for example, if gamma is very large, you will essentially force that all tours, or that the number of tours is minimized. So in this case, since there are 12 points, every tour will contain exactly 4 vertices, and it will look somewhat like this. And then the interesting thing happens once you decrease gamma a little bit and you allow multiple tours to form, or more tours to form than necessary. So in this case, you can see there are now some tours that have only, say, 2 vertices or even just 1 vertex. Because, for example, if we wanted to make this, if we wanted to integrate this point into this tour, we would have to add these pretty long edges. And so this might not be worth it compared to gamma. And then, of course, if you make gamma very small, the problem becomes kind of trivial, because eventually you start getting just singleton tours. So once gamma becomes 0 or small enough that it makes no sense to combine any 2 vertices, you start getting these singletons as your solution. Now, to the best of our knowledge, this exact problem formulation, as I just stated, is new. However, there are several quite related problems, aside, of course, from the CVRP, which I just introduced, which is the main motivation. There are also some other problems, for example, the so-called min-max cycle cover, and there's also bounded cycle cover, which are quite similar and which has received some recent attention. So there have been some recent approximation algorithms with guarantees of 5 and 4 + 4/7. And there's also the min-max version of this problem, so a capacitated min-max cycle cover, where you're trying to minimize the maximum length of a cycle, for which there has also been a very recent approximation algorithm, though with a very, very large factor of over 500. Now, the theorem, which I mainly want to present today, is our main result, which is that given an instance of this capacitated cycle covering problem, we can compute a 2 + 2/7 approximate solution. That's about 2.28 in essentially linear time, if you consider the length matrix as the input. And our approach has 4 steps that I want to briefly sketch out. So the first step, which is actually the last step in the algorithm, but the first step in the analysis, is that there is a relatively simple way of taking any forest. So if you give me any forest in the graph, I can turn it into a cycle covering solution using essentially the edges from that forest. And this uses 2 classical techniques. One is called tree splitting, which you can see used sometimes in capacitated facility location and similar problems. And the other is typical shortcutting that you often see in the TSP and similar settings. So I'll briefly sketch this out in just a minute. And then the main question becomes, what forest should you start with? So you need some forest to create the cycle covering. But if you just start with, say, a minimum spanning tree or something like that, you don't get this approximation ratio. You actually need to find a good starting forest. And this is where we introduce an LP relaxation, which is called the tree cover LP. And we show that you can solve this efficiently, and more importantly, that this LP has some really nice structure to its solutions. And then lastly, I will show that you can use these highly structured LP solutions of this tree cover LP and apply some relatively simple randomized rounding to get this nice starting forest, which we use for this first step here. And lastly, I won't talk about this in this talk, but it's fairly easy to show that this procedure can be de-randomized, and then you get this actual theorem deterministically. Okay, so let me get into the first part, which is how to take a forest and turn it into a cycle cover. Okay, so this, as I said, is the final step of the algorithm, but to understand how our algorithm works, you really have to consider this first. So the idea is you're given any forest in the graph, and you want to create a cycle covering solution using only the edges from that forest. And there are two things, of course, you need to do. You need to obey the capacity constraints. So this forest, it could just be a single tree, which includes the whole graph. So in general, the components here can be as large as they want to be. And the second, of course, is that you want cycles and not a tree. So this is handled in two steps. The first step is what I called tree splitting earlier, which is a technique to turn a forest into a collection of Steiner trees, such that each of those Steiner trees serves the demand of one, by which I mean that the demand of the non-Steiner vertices is at most one. And by turning the forest into this, I mean these Steiner trees, so the edges of those Steiner trees are a subset of the forest, and they're disjoints. So we use each edge as most ones in this process. And then the second step is to turn each Steiner tree into a cycle in the standard way, by which I mean that you walk around the tree in a depth-first way and skip over any repeated vertices and any vertices that are Steiner points that don't need to be included. And this, as you probably all know, is an easy way to turn a tree into a cycle by doubling the edges, or doubling the length. Okay, and of course, one important part here is we want that we don't create too many cycles. So we need to somehow relate the number of cycles that we create to properties of this forest. And to do that, we will maintain on average that every cycle will serve a demand of at least 1/2, except for cycles that come from components of this forest that were already quite small. So the forest could already have a component in it that has a demand of only, I don't know, 0.1, in which case, obviously, there's no way to make that larger since we're restricted to a subset of the edges. Okay, so how does this work? The basic idea, so look at any component of this forest, which is a tree, pick an arbitrary vertex, say this one, and we declare this as a root. So we look at this as a rooted tree. And then all you have to do is you repeatedly do the following. You look at the vertices which have the property that they are maximally far away from the root, and such that the subtree rooted at that vertex, so these are these two subtrees here, these subtrees serve a demand of at least 1. So here it's exactly 1, and here it's a bit more than that. And then you can easily show that you can then find a Steiner tree below this vertex, which serves the demand of at least 1/2. So in this case, for example, let's say we pick these 3 vertices and have this here as a Steiner point, then this little tree here has a demand of 3/4. And similarly, we can, for example, over here, maybe pick this as our Steiner tree, which serves a demand of exactly 1. And then all you do is you just kind of repeat this, and eventually this terminates. And of course, the last, when this terminates, the last tree can be quite small. And so all you do is you do a final check. Can I combine this tree with the last Steiner tree that I created? If yes, then do it. If not, then this shows that the average weight between these two last trees is also at least 1/2. And that's how you guarantee that the average is 1/2. Okay, and then finally, as I said, it's we use the standard technique of turning these trees now into cycles. So for example, for this orange Steiner tree down here, you would walk along the tree and skip over the Steiner point, which is this one, and over repeated vertices to form this triangle. You can do this for all of these guys, and you can see that we create a bunch of cycles, including this degenerate cycle that consists only of the single vertex. Okay, now this gives you the following lemma. So if you start with any forest, then you can compute in linear time a cycle cover solution, meaning a bunch of cycles that cover the whole graph and where the capacities are bounded. And the cost of this cycle cover is given again by the length plus gamma times the number of components. So the length is at most twice the length of the forest. And the number of components has this bound. So this bound is we sum over all connected components of F. So this C of F are the connected components. And we take this U of A, this upper bound on this component. And this is an upper bound on the number of Steiner trees or cycles which we create through this tree splitting. And the upper bound is that if this component is already small, meaning that the total demand served is already at most 1, then clearly we don't need to run this tree splitting at all. And so the number of components will be 1. However, if the component is large, so the total demand is bigger than 1, then we will use this tree splitting, and using the fact that the average demand of every vertex is the average demand of every cycle is at least 1/2, we get that we'll use at most twice the demand many components. So now the goal in the next parts is to find a tree which minimizes this quantity over here, this upper bound. And it turns out that this is actually also hard to approximate, but I will show how to find a solution that gets very close to the cycle covering, the cost of an optimum cycle covering. Okay, so to do this, we will introduce this so-called tree cover LP. Okay, so we need a lower bound on the cost of an optimum solution to the cycle covering problem. And for this, we actually look at tree covering instead. So we have an LP. This LP has a variable xe for all edges in the graph. And it has essentially only one constraint, or one type of constraint. So for every subset of the vertices, for every non-empty subset, we have the constraints. We have the subset here, A. All the edges that are inside this set have to be bounded by the number of vertices minus the maximum between 1 and the total demand. And if you think about the integral points in this polytope, then this constraint essentially guarantees that the integral solutions of this are forests with the special property that every connected component serves a demand of at most 1, because this part of the constraint tells you that inside each set A, you will have at least B of A many connected components. And then, of course, the objective function is just the same as in the cycle covering. So we minimize the length plus gamma times the number of components. And as I just mentioned, the integral solutions of this LP are forests, not cycle covers, but clearly any cycle cover, you can just delete one edge from every cycle to get a solution of this LP. And so this is a lower bound on the optimum. And this LP is actually inspired by an LP relaxation of the capacitated vehicle routing problem, which is almost the same, except we have degree constraints on the vertices that are not the depot. And it turns out actually that this LP relaxation of the capacitated vehicle routing has an integrality gap of at most 3.5, which matches actually the best known approximation algorithm. So this LP is quite interesting. Okay, now the very nice thing about this tree covering LP is that this LP is actually a polymetroid. And because it is a polymetroid, it has a very nice structure to it. So if you take any extreme point solution and you look at a connected component in the support of this extreme point solution, then there are several really nice things that happen. The first is that this support is acyclic, meaning that any connected component of an extreme point solution is in fact a forest, a tree. And there's actually a lot more to it than that, because if you look at there are two types of edges now. There are these dashed edges and these connected non-dashed edges here. The dashed edges are the fractional edges, and these edges here are the integral edges, meaning the edges of value 1. And then you can actually see that there's a way to arrange the components of these integral edges in like a topological order like this, such that if you look at any fractional edge xe, it is actually lower bounded by 1 minus the demand of the component that's on the right here, this unique red component on the right of this fractional edge. So this is the structure of these LP solutions. They look like this. Okay, so now I'll go into how to round solutions of this type. Okay, so recall what we want to do. We want to find a forest which minimizes this quantity, or more particular, where this quantity should be bounded by 2 plus 2 over 7 times the LP. And the important part here, the hard part, is this right part. So the sum of these U functions. This is non-linear. Obviously, we have this U function again is 1 if the total demand is 1 in a component, and it's 2 times the demand otherwise. Okay, and I claim that this can be done through a simple randomized rounding where every edge is scaled up by a factor of 8 over 7, and then you simply sample the edges independently. Of course, this means that the expected length increases by 8 over 7, and if you look at twice the length, you get 16 over 7, which is exactly the ratio that we want. So the only tricky part is showing that this bounds holds for the sum of these upper bounds. Okay. And this is where we use the structure of the LP solution. So if you look at some connected component in the support, and you assume the total demand is bigger than 1, then that means currently the upper bound function, the U of this connected component, is twice the demand, whereas the LP, it turns out, will use exactly just the demand many components. And now, let's say you start by just considering this whole forest, this whole tree, and now for every fractional edge, there's a certain probability that you will drop it if you sample a random edge set. And the point is that if you drop some edge E over here, then how does that affect the sum of these U's? So previously, this whole tree contributed 2 times the demand. But if you remove this edge, you now add the small component to the sum. So that increases the sum of the U's by 1. But on the other hand, you remove the demand of this guy from this big tree. So this means that in total, the maximum increase that you will get is 1 minus 2 times the demand. And this holds even if you remove edges like this. That are somewhere in here, but it's most obvious when you consider edges like this, 2 leaves. Okay. And now, what does that mean? Recall that because of the structure of the LP, every edge is lower bounded by 1 minus the demand. And this means that if you consider the effect of removing an edge, so what is the expected change in the sum of the U's by removing an edge? Well, it's the probability that you remove the edge times this 1 minus 2 times the demand, which we said is the maximum change you can have. And now if you use this, this thing here, then this becomes this upper bound. And it turns out that this is it looks somewhat like this. And you can find a linear approximation, a linear upper bound, which turns out to be 2 over 7 times the demand. And now finally, since all of these sets, these right endpoints of these edges, they're all disjoint, we can see that the expected value of U after you've done this sampling is at most the beginning value, 2 times the demand, plus 2 over 7 times the sum of the demands of all these red components. And so you get an upper bound of 2 plus 2 over 7, the total demand, which is also 2 plus 2 over 7, or at most 2 plus 2 over 7, the demand of the LP. Okay, now finally, in the last 2 minutes, let me get to the conclusion. So there are some other results that we show. So for example, we show that the analysis of this algorithm is tight. So there are instances where this algorithm will compute a solution of cost 2 plus 2 over 7 minus epsilon. So this factor is not just happenstance, it's actually tight for this algorithm. And what's also interesting is this tree covering LP. There's of course a gap between, it's not quite an integrality gap, but there's a gap between the tree covering LP and the optimum capacitated cycle covering solutions. And one might initially guess that this is 2, but we actually show that it is at least slightly larger than 2. So we show instances that converge, where the gap converges to this fraction 2.005. And finally, some open questions. So of course, one open question is what is this gap, and can you improve our approximation algorithm on this problem? And then there are a lot of questions on the CVRP, which, as I said, these LPs are quite related. And for example, we show this interesting lower bound on the tree cover LP. Are there any non-trivial lower bounds on the CVRP LP? We don't really know. And it's also a question if we can use this kind of tree-first approach for the CVRP. The approximation algorithm there is quite different. And then finally, of course, the big open question, show the integrality gap of the CVRP LP is less than 3.5, or provide a better approximation algorithm. And yeah, that's the end of my talk. Thank you for listening.
Thank you, Tom, very much, and very nice talk. Are there any questions? You can raise your hand, or you can write in the chat. There's a question by Sven Jäger. Do you want to say it yourself? Otherwise, I will repeat it from the chat.
Yeah, my question is if you know anything about the problem when you are allowed to cover a node by multiple cycles partially. So, for example, if you have 3 nodes with demand 2/3, and where you
so for the vehicle routing problem, this does actually help. So I said this there's this 3.5 approximation. I think you can reduce this to 2.5 if you're allowed to do this. For the cycle covering problem, we don't know if this helps in this setting. So this is also an interesting question. I mean, yeah, the reason why it works, it helps so much in the vehicle routing is because there you start by computing a tour, and then you split up that tour, and by allowing to reuse vertices, you can split up that tour perfectly. But splitting up the trees, it's not as easy. So it doesn't help so much to like visit this vertex multiple times. So that's kind of the issue.
Okay.
Okay, thank you.
Other questions?
Anybody else wants to ask a question? Mohit? You want to ask?
Yeah, maybe I send it to you on private. But yes, so I wanted to ask about the variant when you have a bound on the number of cycles and there's no opening cost. Like I give you K and you have to open K cycles to cover. Does that make sense?
Yes, I think that's that's one of the related problems that I mentioned. I think that's the bounded cycle cover variance. I think, if I remember it. So there is actually, interestingly, an approximation algorithm with a factor that happens to be exactly twice our factor, but this algorithm does not use an LP and is quite different. So I don't know exactly why this is. This seems like a strange coincidence, but yeah, so there is an algorithm for this problem, which is quite recent, and yeah. But it's a different problem.
But your results do not imply anything for this variant, or do they?
I don't think so, no.
Okay, thank you.
Thanks. Any further questions? If not, then please stay around for some closing remarks. But before, I will unmute everybody to give an applause to Thorben.